already covered derivatives of inverse trig in the previous video, so now we're going to turn to the integrals of inverse trig functions. If you notice, these are the three rules, and if you notice, there's only three of them. Now remember, there's 6 inverse trig functions. There's arcsine, arccosine, arctangent, arccosecant, arcsecant, and arccotangent. But if you notice, there's only 3 rules here. Well, if you remember back to the 6 derivative rules, there were really just 3 different ones: sine, tangent, and secant, and then their cosine, cotangent, cosecant, had the same rule, just with a negative sign. Well, since with integrals we can just pull that negative out front, we can basically just simplify it down to 3 rules, and that's what we've done here. So that's the good news, is that we just have 3 rules we have to learn, and that's arcsine, arctangent, and arcsecant. First of all, it's important to note that the a always represents a constant, and the u is always going to contain a variable. Now, where that's very important is when it comes to the arctangent rule, because since that's a squared plus u squared, you know it does not matter what order you add things in. So it may say 9 plus x squared, or it may say x squared plus 9, but either way, the x squared has to be the u squared, and the a squared has to be the 9, because a is always a constant, and u always contains a variable. As far as the first step to all these problems is to figure out, when you see a problem, which of these rules you're dealing with. So some hints for that. Sine and secant both have square roots. Sine and secant both have square roots. So you see the s relationship there. And secant has something outside the square root. So sine and secant both have square roots, and secant has something outside the square root. And then tangent, t kind of looks like t for tangent, kind of looks like a plus sign, and that's the only one with a plus sign in it. So that's some helpful hints to figure out which one we're going to use. So let's dive in and do a couple examples. Okay, so first one we have is here, the integral of dx over the square root of 4 minus x squared. Okay, this has a square root, so you know it's either sine or secant, or arcsine or arcsecant, I suppose I should say. And since there's nothing outside the square root, it must be arcsine. Now this is just the way I always approach this. Once I get to this point, I write the rule out. So I'm going to write the integral of du over the square root of a squared minus u squared. And I know according to the rule that should equal arcsine of u over a plus c. So my goal is to figure out what pieces go into the rule. So always start with a squared and u squared. A squared is clearly 4. U squared is x squared. So just to be as clear as I possibly can here, a squared is going to correspond to 4, and u squared goes with x squared. So the next step we need to do is find a and u. So a is equal to 2, and u is equal to x. And if you notice, all I did there was take the square root. So there was no derivative or integral or anything like that. I just took the square root of each one. Square root of a squared is a, so square root of 4 is 2. Square root of u squared is u, so square root of x squared is x. Now you do need to go ahead and find the derivative of u, since that's part of the rule. In this case it would be 1 dx. And we need to make sure the du matches. Okay, du equals 1 dx. Well, that's great, because that is what we have on top here, so it's a perfect match. So that means that my equation is exactly in the form of the rule. I don't have to make any adjustments. So that means I can just plug u and a in here and have my answer. So arcsine of x over 2 plus c. And that's my answer. Alright, next up we have the integral of dx over 9x squared plus 2. So this does not have a square root, so automatically you know it's going to be tangent. It's also got a plus, which none of the others have, so it's got to be arctangent. So I'm going to write the rule down here. And this is why I mentioned what I did earlier. A squared has to be a constant. So this time a squared is going to go with the 2, because a has to be the constant, and u squared goes with the 9x squared. So U always contains the variable, A always contains the constant. So now we need to find A and U. A will be the square root of 2. U will be 3x. And then the derivative of U is going to be 3. So we need to check and see if the du matches. Well, if you look, it does not. We just have du and 1 dx, but it says we need 3 dx. So we're going to have to divide both sides by 3. Very similar to u substitution. And we're going to have to put a 1/3 with the du. Well, if we put a 1/3 on that side, we've got to put a 1/3 on this side as well. So when we go to plug it in, we just need to put a 1/3 out front and then do 1 over a arctangent of u, which is 3x, over a, which is square root of 2, plus c. And aside from maybe just combining those front two into one fraction, that's it. So it is important to make sure your du matches, because that may mean you need to put a coefficient out front just like you did with u substitution. Okay, final example. Dx over x times the square root of 4x squared minus 9. You can see here we have a square root, so that tells us it's either sine or secant, and since there's something outside the square root, it must be secant. So the rule for secant is du over u square root of u squared minus a squared is equal to 1 over a arcsecant of absolute value of u over a plus c. Okay, so our a squared is 9, our u squared is 4x squared. That means a is 3, u is 2x, and du would be 2 dx. Now arcsecant is a little more complicated than the other two, and the reason that has to do with the u. We have to make this u match just like we have to make the du match. So we've got to make u and du match. So let's look first at u. This says u equals 2x, but it's all we have over here is an x, so we've got to divide both sides by 2. So actually I'm going to end up getting 1/2 u equals x, so I have to put a 1/2 over here with my u. Okay, now du, it says du equals 2 dx, well I only have 1 dx, so I have to divide both sides by 2, du, 1/2 du equals dx, so I have to put a 1/2 of my du. Okay, well if you notice, what we just did was put a 1/2 on the top and the bottom. Well, if you do 1/2 divided by 1/2, you just get 1, so they essentially cancel out. Now that will happen fairly often with your arcsecant, but it will not always happen, so don't assume they're going to cancel out. Like I said, don't be surprised if it happens, because it does happen a good bit, but it doesn't happen every time. If it doesn't happen, you need to go ahead and divide those two fractions. 1/2 divided by whatever, they can be anything. Just make sure you divide the two fractions if they don't match. So because they cancel out, we just use the rule straight up as it is. We do 1 over a, which is 3, arcsecant of absolute value of u, which is 2x, over a, which is 3. And that will be our answer. So that gives you an example of one of each type of these. The good news is we don't have a whole lot of simplifying to do like we did with the derivatives. So hopefully these will be pretty good for you. So page 393, 1 through 23 odd, omit number 11, was the homework I assigned this particular time. Anything in that range would be good for practice. And I want you to ignore the boundaries. Just find the indefinite integrals. Don't find the definite integrals.